Okay, this is the next session for MapReduce, Yarn, and detailed processing of the mappers and the reducers and all the other components that are involved. So, in my earlier introductions, I've already spoke about HDFS, which is the storage layer. When you put files inside HDFS, the file is broken up into blocks. A typical size of a block is 128 megs. So when the blocks are broken up, it doesn't even look at the line where the line ends. You understand, right? If you have like 1,000 lines and each line is 1 meg, so when you break them into HDFS blocks, when HDFS breaks them into blocks, it doesn't look at, it doesn't respect line breaks. It is just physical breakup. So wherever the 128 meg happens, it breaks it at that point and it forms a block. So that is something which you need to know, because when the application, when the mapper is trying to process that block, it might not see the full line. So in that case, what happens and how it processes the lines and all that stuff, I'll explain to you in detail in the coming session. So that is HDFS. So in a typical HDFS system, you have a name node which has the file system registry, and it manages where the files are stored, like the blocks are stored, and all the file metadata. And there is data nodes where the data gets stored. And usually the typical replication factor is 3, wherein a certain block is replicated 3 times. The next thing is as the rack awareness. If you do not want a lot of network latency, you can store all the replicas in the same rack. So that's the HDFS part. Yarn, yet another resource negotiator. This is the key to running MapReduce, because it manages your availability of map slots and reduce slots. It manages the availability of how much compute is available. It takes care of the scheduling of the jobs. It takes care of user quotas. Like if this user has only this amount of quota, only that amount of compute can be used, and the rest he has to wait in that queue until the compute is available, and that provides the capability of running high priority jobs and all that. The next one is actually writing the map reduce jobs, which is how do you break up a huge file into some meaningful data so that you can actually get some analytics out of it. So the distributed computing paradigm is actually achieved through the MapReduce framework, because you, without even you worrying about how do you start all these jobs and close all these jobs, the MapReduce helps you to write your program, what your user logic is, and then it's been executed into the Hadoop framework. So these are the 3 parts of the story. So I gave an introduction to all the 3. Now I'm going to give you a quick view of how everything works together. So I already spoke about the name node and the slave node. So this is from a compute perspective. So this is the master node, which is the name node, and it also has a resource manager. The resource manager will manage how many resources are available on each slave node, so that you can actually do your processing. The node manager talks to the resource manager to let you know if a certain task has been completed or not, if the computes have been processed or not, and all that. So these are the data nodes. They have the node managers, and there is a map and a reduce slot. If you need to run a map job, then you need to have a map slot. If you need to run a reduce job, you need to have a reduce slot. So these are the map and the reduce slots that are available on each data node for you to do the computing. Okay, so this is how a typical file has been broken up. So if you see, this is a 700 meg file, and each of them are broken up at 128 megs. So there is no line break, like acknowledgement of the line break. It is just physical break. Wherever the 128 meg stops, it stops there. It doesn't even care if it's in the middle of the line or whatever. So that is the representation of this. And if a typical uh, replication for this is always 3. So this is what he's trying to show. So this file has been replicated 3 times in this data node, every block, I mean, of that. And this is the rack awareness. What the rack awareness means is that you want to just put your data into the same rack so that you avoid the network latency. So there is a disadvantage to it, and that disadvantage is if you lose the rack, you lose your data. But but the likelihood of losing a machine is high than losing a rack. So that's still a viable option so that you can have your low latency options available. So that's what this is talking about. Sorry. So now I'm going to, in the last session, I gave an introduction of the map job. So map and reduce and how this happens. So that is, this is a representation of how the map and the reduce actually happen. So when you take a file and now you want to do the mapping and the reducing. Mapping is you read a physical entry in your file and actually convert it into a computable form, like a key value pair. So that is very important because you need to process that data in a way that your program understands. So if you see this, your file, your data block is broken up into input splits. An input split is a one which actually understands the line breaks. If you see you have 128 megs and it has 2.5 lines, but your input split is not, it's not 2.5 lines, it is 3 lines. So the remaining half line, the input split will go get it from the other block and actually build a split. So these splits are actually passed on to your map job. You can't actually put a physical block into a map job because that will not help because you can't process that data. So that's what this is trying to show. A split is a logical separation. That means you have 3 lines, 5 lines, 10 lines, and you can actually have a max and the min input split. So if you want to run a huge map job and your data block is very small, then you can actually increase your input splits to like, let's suppose 5 data block size. And you can create a huge map job. In that case, what happens, it will go get the rest of the blocks and it'll put them together and provide you an input split for your map job. So that is the configurable part in your program that you write. So there are parts of the map task that's been explained here. A record reader transforms the input split into records. So how the split is actually built is based on your file input format. If it's a binary format like a sequence file or a zip file or whatever, or if it's a text file. If it's a file input text file, then the input split knows the end of line character and it can build the split. And the record reader here, what it's actually doing is it's reading each record and it's passing that record to your map program. So that is what the record reader does. So the first step is the data block, which is a physical breakup of 128 megs. The second part of it is the input split, which actually understands the record endings and it actually builds a block of data that you can pass to the map program so that you can process that piece of data. And the next one is the record reader. From that input split, it will extract one record and it will pass it to the map. And what you do in the map is a user-defined function. So if you are trying to do a word count, then you write a map in a certain way. If you're trying to do something else like in our cases, we try to transform from one format to the other format, or we're trying to at least extract the high frequency words from that. So there are different maps that you can write. So you can write multiple user defined functions. You can write many maps and you can actually chain the maps into your process. So all that is actually part of the map process. So once the mapping process is all done, then the data gets written into the same data node. If you can see, it's not written back into HDFS, but it's written into the local file system, intermediate store, output store, into the local file system of your data node. The reason they don't write it to HDFS is because it gets replicated 3 times again, which is not useful because it's just a piece of data that has been formed after your mapping process. And all this data moves into a shuffle and sort. What shuffle and sort does is it brings all the keys of a mapping process together so that it can be processed together. So if I want, in my previous example, I've explained about word count. And in word count example, once again, I'll bring back the word count example. Yeah. So just a quick view of the word count. So in this case, this is my input split. My input split is being split into each record by the record reader, and then the every word I have counted how many times that word has happened. So deer is one, bear is one, river is one. So I just, even though car and car are still there, I'm not combining them. You can use other processes here which can combine the results so that you don't ship a huge amount of data for your shuffling and sorting process. But in a typical map, whatever word comes in, you just count how many times that is there. So these are all ones. That's what your map function is doing. Get a word and stick the value as one. And in the shuffling process, all the keys that are there, it's brought together. So this key bear has one and one. So there's a one value here and there's a one value here. All of them are brought together. That is called a shuffling and sorting process. And this shuffle and sort is actually passed on to your reduce process, which will combine these two to count how many bears are there. So it's adding up all the counts, all the values to actually build the word count. So going back to where we were, so all the intermediate results that I've shown here, right? The deer, bear, one, all this is actually stored in the local file system. And this local file system data is moved to the reduce box wherever it's doing the reduce and sort and shuffle, sort and shuffle. This sort and shuffle process will bring the keys together and it will pass it on to the reduce process here. And the results of the reduce are actually saved into HDFS because this is the outcome of your program, and that's why it needs to be replicated. So the combiner here. So what the combiner means is if you have in this example, you have bear, you have, let's suppose you have car and car here. Instead of sending car and car and car, like if let's suppose this inputs from all these input splits, if you get a huge mapping thing which has only one word, then you're actually sending a huge file across the network for your shuffling process. Instead, you can actually combine all of them together and say car, I have like 2,000 occurrences. That means you're just sending only one record instead of thousands and thousands of records across the shuffling process. So what that is actually combine is doing is actually reducing your network latency by doing a localized reducer. So what it's doing is taking all the data that you anyways are going to reduce in the future stage at an earlier stage after your map process so that you reduce the amount of data that passes through from the network from the map process to the shuffle and sort. The next one is the partitioner. What the partitioner helps is actually trying to it comes up with how many number of partitions you need to process at the end of the process. So in this case, we got very little data. It's not a lot of data, but in a typical map process, sometimes you explode that data. So even if you get a one-line record, you might explode that data into thousands and thousands of records. And when those thousands and thousands of records need to be processed, you want to expand on your reduce process so that you can do it quickly. That's when the partitioning is useful because it will help you to define how much a shard is going to be for your reduce process. So that's what it's doing. It pulls the intermediate key value pairs from the mapper. It splits them into shards, one shard per reducer. So most typical ways that we do in Spark or whatever, the input split, whatever we get is very small. Like it's not very small, but it's not exploding. But once we start processing that data and we want to explode it, we repartition it into a huge amount of processes like shards so that I can put more compute and reduce all of them in one shot. So that's what we usually typically do, which is called the partitioning. We repartition the data, wherein we actually increase repartitioning it to a high number, or you can coalesce it. Coalesce it is actually reducing the number of splits. We don't need so much splits because each shard is not big enough. So then you coalesce it. There either you can explode that size or you can implode that size. That is typically done by a partitioner. The next task is reduce task. In the reduce task, the first step that happens is shuffle and sort. You are not doing the shuffle and sort. It's the framework that does the shuffle and sort. But what the shuffle and sort means is bringing like keys together and passing it to the reduce process. And the sorting is so that it can put equivalent keys. So the purpose of the sort is to collect the equivalent keys together. First, it needs to sort so that you can put the equivalent keys together, and the shuffling is actually bringing them together. And what it also does is actually it appends to it. That's why it sorts it. So what the shuffling process does is it's not when it builds the shards, it keeps appending tasks to it instead of modifying it. So I'll explain a little bit more in depth of shuffle and sort, because it needs a lot more understanding of the map reduce before you get too much in depth into shuffle and sort. The next one is the reduce, which I've actually explained a few times. So once you get all the values, key values that are there, your final step is actually the reducing. Is your final, what the final outcome of your analytical job is going to be. So once you've got the data into a computable form, this is where the actual computation happens. Wherein you reduce it, that means you're actually processing the data to produce the outcome of the result. So that's, and the output format is dependent on what your reduce process is going to be, what the outcome is going to be. So most typical output formats that we build is Parquet. We don't build text. Parquet is the columnar storage, and that's very good because it's highly compressed, and it has many more advantages. One is the compression, one is the size of the storage, and also it also has a schema. So you don't have to actually build another schema. Your text files have no schema. So or your map reduce job is very, very specific on your text file, and it has to write how the text file is built. If it's a comma separated file or if it's a pipe separated file and all that. Parquet, a schema is already there as part of the Parquet file that you save. So that's a very typical output format that people in the industry do. Everybody compresses it. Either they use gzip or lzip or whatever zip, but everybody compresses their data and stores it into HDFS because it's such a waste of space if you don't compress the file. The last one is Yawn. So this is the one which helps you to actually run your MapReduce job. So here the client submits the job to the resource manager. What the resource manager does is identify all the resources that are available in the space and actually put the identify and start the application master. What application master is the driver of your MapReduce program. So you have three parts that you typically write in your MapReduce. One is the driver, which tells you when to start what are the series of events that happen in your in your program. So I want to run 3 maps and 2 reduce processes and all that. So when you write your driver, that's where you actually mention, okay, this step I'm actually doing my mapping, and this step I'm actually doing my reducing, and then this output of this reduce goes into this map, and all the series of steps to do. It's like typically like your recipe, and each step is actually a task of your recipe. So that's so the first step for executing your map reduce is to start the application master. So it identifies the node where an application master can be spawned. That's where the here once the application master has been spawned using the help of the node manager, it talks to the resource manager to start the rest of the map and the reduce tasks that are part of the driver program. And this it does in conjunction with the resource manager and the node manager. What the node manager talks to the resource manager is to tell if the map task is successful or the reduce task is successful. It doesn't tell the application master. It goes all the way back to the resource manager, and the resource manager will start executing it. So if the application master says start my map process, then it talks to the node manager and it creates a container, and then the status of these containers are communicated back to the resource manager. And this manages all your map reduce tasks in conjunction with your application master, which actually tells the resource manager what needs to be executed. And the resource manager has 2 pieces. One is the scheduler. So you don't want to run your jobs always at the certain time. You can actually cron it, or actually you can actually schedule it. And if the entire cluster is full, then you actually are sitting in the queue. All that is managed by the schedulers and the application managers. So the application manager is different from the master. Application manager is actually accepting your jobs, and it's negotiating with your application master to run the MapReduce job. So when I was talking about the application master talks to the resource manager, it's talking to the application manager and the resource manager. Yeah, it is very confusing to have the same names, but I'm sorry, but that is how they have come up with. And if the driver fails, then it will restart your application master, and it negotiates the resources and tracks the container status. All that stuff is actually uh, done with the by the application master in conjunction with the application manager. And the next one is about Yawn. So multi-tenancy means multiple people trying to run their jobs. So it's not just one user trying to run your job, it's multi-user trying to run your job. That's what multi-tenancy means. That's why you have coders. That's why you have what is that, user managed queues. So if you have a queue of 10%, only this user can use this queue of that 10%. So there is a certain amount of security and code is available, and that's why it's a perfect candidate for multi-tenancy. It takes care of the Yarn takes care of the cluster utilization. So how well the cluster has been provisioned. So let's suppose if you want to run 100 jobs, and it makes sure that all the clusters utilized to the 100%, and then it keeps rest of the stuff into the queue, and when the resources are available, it will schedule those jobs. The next one is scalability, because now before the node manager used to be overloaded with all the stuff. Now you have a resource manager, the application clusters move to the nodes now. So there are a lot of things that have been improved so that everything is not sitting on one computer, but it's actually dispersed into many smaller processes to increase the scalability of the process. And it is compatible. So nobody runs Hadoop 1 anymore, but it's compatible. That's what they're trying to say. So this is the high level that I wanted to talk about. I'll go in depth with input splits, but for now, I'll just take some questions. I'll stop the share, but I'll stop the recording, and I'll take some questions, and then I'll continue into the input splits.